My pleasure to introduce our invited speaker, Dr. Akash Kumar. So, Dr. Kumar is a cross-appointed researcher and assistant professor at University of Gothenburg, Sweden, and Tohoku University, Japan. He earned his PhD in 2020 from Indian Institute of Technology, Delhi, India. His current research centers on spin-Hall nano-oscillators with a strong focus on their mutual synchronization and use in unconventional computing applications, including neuromorphic and reservoir computing. So today he is giving a nice talk on the topic Scalable and Programmable Spin-Hall Nano-Oscillator Networks from Phase-Tunable Synchronization to network of 100,000 nano-oscillators. So please join me welcoming Dr. Akash Kumar. Dr. Akash, the floor is yours.
Can you see my slides?
Yes, yes.
Are they in the correct mode?
Yeah, yeah, you can
Great.
start. Thank you.
Okay, somehow I can't see them. Okay. This is very strange, happening for the first time in Zoom. Yes, I think now it's good. So thank you, everyone. And thank you, Pankaj and Nivedita, for inviting me and giving the opportunity to present our work. So thanks for the introduction as well. And as Pankaj has already told you, I'm going to talk about spin Hall nano-oscillators. And particularly, I would like to show you that we are developing this emerging devices as a platform for unconventional computing. And without any delay, let me delve into this thing. Okay. Uh, so before I go into science, I would like to thank the whole Applied Spintronics group, both at University of Gothenburg, Sweden and Tohoku University, Japan. Here I show you the faces that are part of the group right now. Some of them have directly contributed to the work that I'm going to show today, and others are actually doing great, and you will see them presenting really nice work in future. I would also like to thank the funding agencies without which this work was not possible. So this will be the outline of my today's presentation. I will first start with the introduction of the field, and then I talk about what spin Hall and oscillators are, give you a status update of mutual synchronization, and how can we achieve a variable phase mutual synchronization that can be used to transmit information between oscillators along with their mutual synchronization. Then I will show you the programmability of these spin Hall and oscillators using voltage and memristive control. And then finally, I will demonstrate the scalability of this whole platform, which is not possible or which is restricted in other systems before summarizing my presentation. So I'm sure that we have all seen this graph before. It shows that how the energy consumption by information and communication technology is going to be more than 21% by 2030. And this research was actually conducted in 2015. So if we count on artificial intelligence and Internet of Things into this graph, this number is going to be even exaggeratedly higher. Now we are left with two options. Either we start putting new nuclear power plants, solar power plants, or wind turbines to provide more energy into the system, or we basically think, how can we do the computing in slightly different way, at least for some of the energy hungry problems, such as combinatorial optimization problems. And that's where the new non-Neumann architecture of computing comes in. Quantum computing is one such example which can be utilized to solve some of these energy hungry problems in which conventional computers are not able to handle. But the quantum computers require low temperature operation. So bringing it to our personal computers, mobile phones, or laptops is going to be highly challenging. Now, researchers in spintronics and also in other technologies such as memristors or ferroelectric memories or two-dimensional materials are trying to look for alternatives at room temperature. These alternatives range from neural networks to reservoir computing to Ising machines, where basically what you do is that you put this hard problem onto your physics-informed system in the form of spins, qubits, p-bits, or d-bits, whatever your system allows you to call it, and let your system solve it by the nonlinearity of the system itself. And that the ground state of the solution of this physics-informed system is basically a probabilistic solution for your problem. Now, what is common with all these different alternatives is they require a large number of nodes, p-bits, qubits, d-bits, or whatever you want to call them, individual control of these nodes so that you can easily map your problems, and an interconnectivity between these nodes so that they can solve each other. And when I say interconnectivity, it doesn't need to be, it actually should not be restricted to the nearest neighbor, but we should also have coupling between large distances. Now, we have recently put forward a technical review of spin-based computing, where we have pointed out how different spintronic technologies are trying to solve these problems. Now, in today's presentation, and eventually in this whole conference, we are focusing on the spintronics. And the reason is simple. The spintronics allows you to have the spintronic devices basically operates on the manipulation of magnetic states. And compared to any other technology, these magnetic states can be manipulated by various means with magnetic field, charge current, heat, light, voltage, even stress and strain. And on top of that, most of the spintronic devices, not all, are CMOS compatible and room temperature operation. So it is a bit easy if we can demonstrate something with spintronics and develop something, we can bring it to our devices or our personal devices pretty easily compared to quantum computing. Now, this slide is not new to the audience, in my opinion, but let me just revise it. The field of spintronics started with the discovery of giant magnetoresistance, where researchers, Professor Albert Ford and Professor Peter Grunberg's group, demonstrated that you can tune the resistance state with the help of the magnetic field. It happens because of a spin-dependent tunneling, changing the having different resistance state for anti-parallel alignment of the ferromatic layer and a parallel alignment of ferromatic layer. So in this way, you can change the resistance bit using the magnetic field. And this was the discovery that changed the hard disk at that time and changed the way how we stored the information. However, if you want to make memory of these kind of this technology where you are tuning using magnetic field, it becomes really difficult because you cannot have a small magnetic field or magnetic field for each and every bit. So that's where the spin transfer talk comes much more handy, where you can actually manipulate the magnetization, which you were previously doing by applying magnetic field, now using a charge current. And charge current is pretty easy because you can have different parts of charge current in very large arrays of memory bits. So what happens in this, basically, when you pass an unpolarized charge current through a ferromagnetic layer, which we also call a polarizer, this charge current gets spin polarized into this direction of magnetization and then exerts a torque on the next magnetization. Either it can start oscillating or you can switch the magnetization. We will talk about it in a bit. Now, in past decade, researchers are actually focused towards spin Hall effect, another method of generating polarized spin current or pure spin current without the need of a ferromagnet. So here in spin Hall effect, you can generate such spin polarization using heavy metals and demonstrate switching or oscillations. Now, how does actually spin transfer torque or spin orbit torque acts on the ferromagnetic material? To understand that, we have to look at the LLGS equation and see that when we place a magnetic material in the presence of a magnetic field, it experiences two independent torques. One is the precessional torque, M cross H. The other is the damping torque, which comes from the intrinsic ferromagnetic materials. What happens with these two torques is that precessional torque gives a precessional motion of to magnetization around magnetic field, and damping torque tries to align the magnetization in the direction of the magnetic field, finally giving rise to a spiral motion of magnetization and final alignment. Now, in the presence of STT and SOT, you can actually compensate this damping term. If you choose the charge current direction in such a way that you are compensating, you can slow down this damped motion. Now, if you have sufficiently high current and high enough STT or SOT, you can actually compensate this whole term and you get ended up with this precisional term. Your magnetization start processing with sustained auto oscillations. Now, if you have a bistable magnetization, if your magnet can also stable in the other direction, and you still apply some more STT, you can actually switch the magnetization. And this is the basic principle of the memory devices, whether it is STT or SOT, depending upon the technology. And this is the basic principle of the oscillators that I'm going to discuss today. Now, based on the phenomena of generation of spin current, whether it is STT or SOT, these devices are known as spin torque nano-oscillators or spin Hall nano-oscillators. As the dimensions or the schematic shows clearly, the STT-based devices requires a charge current flowing perpendicular to the plane. The spin Hall nano-oscillator-based devices require charge current flowing in the plane for the same spin polarization. Now, once you have the torque acting on the magnetization and you have sustained auto oscillations, thanks to the magnetoresistance, as you see here, which basically shows us alignment of the charge current versus the magnetization, we get high frequency signal when this auto oscillation happens that you can measure using either an oscilloscope or a spectrum analyzer. Now, the first spin torque oscillator was demonstrated in 1999, actually, and in 2003, the first FTNO was fabricated using a spin valve-based geometry. Here, what you see is that the magnetoresistance converts the auto oscillations into an electrical signal that you can measure. These devices can be nanoscale, up as small as 10 nanometers. They are low energy consumptive compared to other technologies, and they are fast. If you look at their frequency, they can be from 100 megahertz to 60 gigahertz easily. One of the important factor comes for unconventional computing aspect is the nonlinear operation. If you look at the frequency of these devices, initially it doesn't change with charge current, and then suddenly you see a very negative change in the frequency. Another important aspect for communication application is the high tunability of these devices. You can tune the frequency with both charge current, as you see here, and also with magnetic field, where basically the frequency follows the FMR curvature of the ferromagnetic material. Now, because of these properties, these devices have potential application in RF wireless communication, microwave assisted hard drives, wave-based computing, neuromorphic computing, Ising machines, as well as recently demonstrated energy harvesting. Now, what happens in nature when you have such a nonlinear and oscillating system? We see very mesmerizing patterns such as flocking of birds or firing of fireflies in a very resonating mode. Now, same thing happens if you put two spintronic oscillators nearby. They start talking with each other and start mutual synchronizing, resulting into lower line width, a higher output power, as you see here. Initially, we had two independent signals, but then they got locked and gave rise to higher output power, which also you can see here. Now, the mutual synchronization and the spintronic oscillators were demonstrated to also have reservoir computing or neuromorphic computing kind of properties. In 2018, from researchers from CSIS Thales demonstrated that you can utilize a number of oscillators to do a reservoir computing, where they demonstrated how you can detect French vowels. What they basically did is that they had four oscillators in series, and these four oscillators generated four signals: one, two, three, and four. Now they have implemented these French vowels onto unknown frequencies FA and FB in the similar range as of the oscillation frequency. Now, when you pass this unknown frequency into this field line that you have on top, this field line get injection locked with the oscillators. Now, depending upon at which point this FA or FB locks with your oscillators, you can detect the frequency because you already knew your frequencies of your own oscillators. For example, in this blue curve, the FB signal locks with the fourth oscillator and gives rise to a larger output power. And this injection locking can be seen here, the 4B injection locking. So in this way, by looking at the injection locking patterns, you can detect which French vowel it was. However, if you look at spin-torque nano-oscillators, the biggest problem is their fabrication. You not only have to fabricate ultra-thin films with a very thin barrier, but you also have to do a very complicated fabrication of having a bottom electrode, a top electrode, a nice encapsulation around the spin-hole nano-oscillators. Sorry, spin-torque nano-oscillators, which makes their mutual synchronization very challenging, coming from the complex interconnections, one-to-one connectivity, and individual control. And because of all these reasons, up until now, only 8 STNOs has been mutually synchronized. Now, the problem is that if you want to do any unconventional computing, you need large number of oscillators. 8 STNOs is not going to work in a real life system. So the simple question comes is that can we scale these systems to a large number of oscillators? And my answer to this is that if you use a spin Hall nano oscillators. Now, what is the spin Hall nano oscillators? Let's jump onto that. The spin Hall nano oscillators basically utilize the spin Hall effect phenomena, where you use a non-magnetic material with high spin orbit coupling. You pass a charge current into it. The spin current, because of a non-relativistic magnetic field in this material, gets deflected into two opposite directions, resulting into a spin polarization at this interface. Now, this polarized spin current acts a torque, as we discussed previously, and can sustain auto oscillations. The first spin Hall oscillator was demonstrated in 2012, where researchers basically what they did is that they fabricated a micro disk of this non-magnet ferromagnet, as you see here, permalloy platinum. And then on top of that, they fabricated two gold contact pads with 150 nanometer thickness and a small nano gap between them. Now, what happens is that since gold has low resistivity and has pretty high thickness here, most of the current goes through the gold contact pad until it reaches to this nano contact. And as soon as it gets reached to this nano contact, most of the current goes to in the bilayer, resulting into very high charge current density into this nanoscopic nano gap region, resulting into larger JS and hence larger torque and sustaining the auto oscillations that were observed using BLS in this particular case. Since then, various spin Hall and oscillator geometries has been demonstrated, whether it was nanopillar or nano gap or nanowire, where actually researchers fabricated the bilayer system into a nanowire shape to generate that large charge current density. The one distinct geometry came as nanoconstriction in year 2014, where researchers fabricated initially the micro disk of this or micro bar of these bilayers, but in the center, they made a nanoconstriction. This nanoconstriction allows you to have higher current density in this particular region and sustain auto oscillations. The good thing about this nanoconstriction oscillators is that they have a single excitation, a coherent single excitation, compared to if you look at the nanowire. Now, because of that, these oscillators are also widely frequency tunable, similar to STNOs. They are also highly nonlinear. As you see, the frequency changes highly negatively here with charge current. They are CMOS compatible. The in-plane current flow compared to STNOs allows a very easy nanofabrication and a coherent single excitation in nanoconstriction geometries, a rich coupling because the ferromagnetic material can be shared, and a direct optical access. For example, if you want to do BLS measurement, which is not possible for STNO-based systems because you have a very thick contact pads on top of the material. So you can also optically look at what kind of modes these are generating. Now let's come to my actual work. So we started with these nanoconstriction spin-Hall line oscillators with a width of 10 to 200 nanometer. In our lab, we usually utilize the heavy metals of tungsten, platinum, tantalum, or their alloys. And at the same time, we utilize ferromagnets such as CFB, nickel iron, cobalt, or their alloys. Now, once you have fabricated this device, the measurement is pretty simple. You put a charge current through a bias-T into the system. You get the spin torque. You apply the torque on the magnetization. The magnetization starts auto-oscillating, and you measure it using the spectrum analyzer. This is one of the first devices that I fabricated as a postdoc in year 2021 when I joined University of Gothenburg. And if you look at the signal, this is what it looks like. A high frequency signal in few gigahertz with a line width of pretty low or resulting into a quality factor, which we call as frequency divided by line width. So if you divide frequency by line width, you get a quality factor of more than 1,000. This is highest for any nanoscopic oscillators operating with this such charge current density. Now, the interesting thing comes when you look at the frequency versus charge current dependence of these oscillators. So what you see here is that a highly nonlinear operation of the oscillator. There is a range in which the frequency doesn't change with charge current, and then suddenly there is a range where it changes negatively. And then it again starts changing positively. Now, this is very interesting. Like, how can a simple device have such a interesting nonlinear properties? Now, the answer is if you look at the mode generation in these oscillator devices. So these different nonlinearities can be described here, and these are the modes that result into it. And if you look at the snapshots from micromagnetic simulations, here I show you different snapshots for a 0 degree, where basically the magnetic field was applied in the plane, compared to 85 degree, where it was almost out of the plane. And then here to here, we go with the magnetic field, a very low magnetic field of 0.1 Tesla and almost 1 Tesla of magnetic field. Now, what you see here is that for a low magnetic field, 0.1 Tesla, and an in-plane magnetic field, the auto oscillation starts at the edge of the nanoconstriction, resulting into negative nonlinearity. And then as you go towards the higher magnetic field and higher out of plane angle, they start localizing in the center, resulting into a no nonlinearity. And then if you provide very large out of plane magnetic field and large magnetic field strength, you start getting a propagating mode of the oscillators, resulting into a positive nonlinearity. So these different nonlinearities can be understood by looking at the different nanoconstriction modes that you are generating. Now, coming back to the fabrication of these devices, it's pretty simple. You define your nanoscopic nanoconstriction using an E-beam lithography, and you do the argon ion etching. Now, thanks to the charge current flowing in the plane, you can have now multiple of oscillators by just having a wider bridge between them. Now, this wider bridge, what does it do? It basically reduces the charge current density into this region, separating out the upper oscillator and below oscillator. Now, in this fashion, you can have as many oscillators as you want. You are not restricted with complex interconnections. You can have 10 oscillators or 20 oscillators or 50 oscillators in a chain. And you're not also restricted with chains, but you can also have two-dimensional array of oscillators. For example, here I show you 20 cross 20, that is 400 oscillators. Now, mind you, when I started with spin torque nano oscillators, it was 8 oscillators that has been mutually synchronized. And here I already show you 400 oscillators. But wait until I go to the last slide that I want to show you. So let's look at what is the status update of the mutual synchronization of spin-Hall and oscillators. Now, first mutual synchronization study of spin-Hall and oscillators was demonstrated in our group in year 2017, where we mutually synchronized 9 such spin-Hall and oscillators. Now, the general question might come that how can you synchronize much larger number of oscillators compared to STNOs? Now, the one thing is that we do not have such a complex interconnection. But the second thing that comes in the picture is the electrical coupling or the different coupling mechanisms of oscillators. So for spin torque nano oscillators, the electrical coupling was the only coupling mechanism. That is, the signal generated by the first oscillator goes to the next one and to the next one. However, spin-Hall line oscillators not only have electrical coupling, that is the oscillator signal generated by this one goes to the next one, they also share a ferromagnetic material between the oscillators, which basically allows the overlap of the magnetic moment, having a propagating spin wave based coupling or propagating mode coupling. At the same time, you can fabricate these oscillators much nearby to each other, resulting into dipolar coupling. So in this particular work, we have demonstrated that we can synchronize 9 such oscillators, resulting into higher output power and lower line width. Later on, I wanted to study even larger number of oscillators, so I started optimizing the ferromagnetic material. I optimized tungsten CFP MGO. At the same time, I optimized the separation between the oscillators. And for a 200 nanometer separation, I could actually mutually synchronize 21 such oscillators, resulting into 1 by n decrement in line width and 1 by n square increment in peak power. Now, if I show you the signal for these oscillators, this is what it looks like. For tungsten CFB MGO system, this is what the signal looks like. We can synchronize up to 21 oscillators with higher output power. And at the same time, we can synchronize in-plane magnetized system with higher output power. If you look at how does the synchronization looks like where and the line width and peak power, this is what it looks like. We initially start with unsynchronized modes, and then once we synchronize, we result into a lower line width, whether it's CFP-based systems or a nickel-iron-based system. At the same time, in this particular region, the output power also becomes higher. And this is what we have already discussed. The line width, when they mutually synchronize, decreases with 1 by n, and the peak power increases with n square. The quality factor in this particular case increases linearly because your line width is going linearly down, right? Now, looking into this, we moved forward from 20 oscillators. I fabricated 50, 30, 40, 50 oscillators. But what we observed is that, for example, for 30 oscillators, if you look at here, for this particular current that is 450 microamp, there are two signals that our oscillators are not synchronized. However, you see there is a very low line width in the signals, and also the peak power is much higher than the actually mutually synchronized signals that are here. They are not so powerful, and the line width is much broader, which basically means that there is a collective dynamics between the oscillators that restricts the mutual synchronization above certain number. Or maybe there is a heat in the system because we are passing more and more charge current, which results into more thermal agitation, breaking the mutual synchronization into partial mutual synchronization. So I can say two things here. One, although we cannot have a robust mutual synchronization, we still have a single coherent mode, which basically shows that the oscillators are talking with each other, although they are partially mutually synchronized. Now, the next thing was that can we actually control the phase of these oscillators? So I demonstrated that we can robustly synchronize large number of oscillator chains. But can we have a one-to-one coupling between individual oscillators? Because that is something very important for unconventional computing domain, right? So for that, we have to actually invoke the propagating spin waves because spin waves are known to carry the information, right? So if we can attain a mutual synchronization where spin waves are the dominant mechanism, we can actually pass information between oscillators. Now, to have propagating spin wave based mutual synchronization, we need two things in the system. Number one, we need spin waves in the system. Second, the spin wave coupling should be dominant over the other coupling mechanisms. Now, to get spin waves in the system, you have to have large positive nonlinearity because spin waves can only be attained when your operation of frequency is higher than FMR frequency, and that only happens when your nonlinearity is positive. Now, you're looking at this analytical calculations, we got to know that we can attain large positive nonlinearity for a high PMA field materials. At the same time, so this is what is utilized by Himanshu Flora in 2019 to demonstrate that we can actually have propagating spin waves in the system. That is, your frequency of operation, as you see here, lies above the ferromagnetic resonance of the system, confirming that the PMA-based tungsten CFB NGO can sustain spin waves. So first condition is fulfilled, right? Now the second is that how to have spin waves as the dominant coupling mechanisms. Now the answer to that lies into this analytical calculations done for nano-contact STNOs around in 2005 by Professor Slevin and Trubowicz, where they demonstrated that so first of all, I have to give you a note here that this analytical calculations were done for nano-contact STNOs. But nano-contact STNOs also share a ferromagnetic material between each other. So the same calculation very well fit to the spin-Hall nano oscillators. And what does this tell us is that around 500 nanometer of separation, we get the highest spin wave based coupling compared to the magnetodipolar coupling. Now, utilizing these two things, I fabricated new devices where I utilize the perpendicular magnetic anisotropy of tungsten CFP MGO. And with the lithography, I fabricated these devices with 500 nanometer or more separation. When I looked at the power spectral density of such oscillators, what I see is that there are different regions of mutual synchronization. The first region where the oscillator doesn't synchronize, they're unsynchronized. The region 2, where they robustly synchronize and result into highest output power, which is very good and very common with our previous studies. Now, then we end up in a region 3, where we do not see any output power. Now, this can happen for three reasons. Either the oscillator is going to die because of heat or because of large current density in the system, as all our spintronic devices die at some point of time, which is not possible because when we increase the current to 0.8 or 0.78, we again get to a region 4 with higher output power. So that was not the case. The second thing is that there might be an oscillation death, which basically means is that both of the oscillators share the energy in such a way that they increase the threshold of the oscillators, resulting into no oscillations into this particular range of current, which may or may not be possible. But for that, we have to look at the other aspects. Now, the third thing possible is that both of the oscillators go anti-phase to each other. So basically resulting into the cancellation of their magnetoresistance response. Now, to confirm that this is coming from spin waves, I measured an in-plane magnetized system where we only see region 1 and region 2, no synchronized region or unsynchronized region, and a robustly mutually synchronized region. Now, to look and understand this more, we perform some micromagnetic simulation by putting the experimental data from the auto oscillation measurement and spin torque ferromagnetic resonance measurement about the thin films. And this is what we see. We indeed reproduce this region 2, region 3, and region 4 in simulations. And why does it appear? If you look at carefully the phase map of the oscillators, what we see is that region 2 and region 4, where we observe higher output power, both have in-phase mutual synchronization. The phase of these oscillators is same. However, in the region 3, the phase of these oscillators becomes anti-phase to each other, resulting into no output power. Now, this basically gives us a direction that it is coming because of anti-phase mutual synchronization. Now, to confirm this experimentally, first we have to rule out the oscillation death, right? So for that, we first perform the phase resolved BLS measurement. In this, we scan the laser of the BLS and look at the magnon intensity at different oscillator systems. So this is the region of oscillator 1 and this is the region of oscillator 2. Now 0.4 basically is in this region where we see that one of the oscillator is oscillating at this frequency. The other oscillator was actually at the different frequency as you see here. At 0.5, somewhere here, both of the oscillators are in phase in this result, and somewhere here, the oscillators show large magnon intensity. However, at 0.75, where we have this third region, we again see that both of the oscillators has large magnon intensity. This basically confirms that both of the oscillators are actually operating and oscillating, but they are not in phase. To further confirm experimentally that they are out of phase, we performed something called phase resolved micro BLS measurements, in which what we do is that in the simple BLS, we inject another signal of the same frequency as of the SHNO frequency. Now, this helps us to lock the injection lock the spin Hall and oscillators. Now, the good thing is that we can control the phase of the incoming signal using an electro-optical manipulator. Now, thanks to that, we can tune the phase of the injection locking signal. And when the phase of the injection locking signal matches with the phase of SHNO, we are expected to see higher magnon intensity. And when the phase of the injection locking signal is anti-phase to the spin Hall line oscillator, we are expected to see no magnon intensity. And when we looked at the maps, this is what it looks like. So in region 2, where we had higher intensity, for a 90-degree incoming phase of the injection locking signal, both of the oscillators show high magnon intensity. This basically confirms that not only both of the oscillators are in phase for this particular system, but they are also in phase to the 90-degree incoming phase. And when we change the incoming phase from 90 degree to 270 degree, none of the oscillators shows any signal. This confirms that oscillators are in phase and locked with 90 degree. Now, when we went to the region 3, where we saw this anti-phase synchronization, for a 90-degree incoming signal, the oscillator 1 doesn't show much intensity. The oscillator 2 shows much larger intensity. And when we go to the 270 degree, this gets reversed. The oscillator 1 shows much larger intensity now, and the oscillator 2 doesn't show anything. This confirms that at this particular current, both of the oscillators are anti-phase to each other. To confirm further, we are again measured at 0.75 milliamp, where we again observe the same thing. The first oscillator doesn't show any intensity, the second shows large. And when we invert the incoming phase of the oscillator, the first one shows large intensity, the second one doesn't. This confirms that we can actually attain a one-to-one coupling between the oscillators and tune between the phase. Now, how controllable is this phase actually? So we did these measurements over different current ranges. And what we see is that with the change in charge current flowing in the system, you can change this phase difference from 0 to 180 degree, basically completely controlling the phase of the oscillators. Now, one simple that you might be thinking that why does it actually happens? The simple reason is that when we change the charge current into the system, the wave vector of the spin wave changes, resulting into a constructive and destructive interference of the spin waves between the oscillators, resulting into in-phase or out-of-phase mutual synchronization. Now, question was that here we demonstrated for 500 and 700 nanometer. Can we go beyond that? The answer is that yes. If we fabricate devices with 1 micrometer or 2 micrometer, we can still observe same in-phase and out-of-phase mutual synchronization. This confirms that we have a long-range spin wave variable mutual synchronization where we can control the phase on demand. But then when we sent this manuscript for review, one of the reviewers asked that, okay, you have this nice individual control or nice control of phase, but can you individually change one of the oscillators instead of changing both of the oscillators? Because presently we were passing a charge current, which changes the signal or the phase of both of the oscillators at the same time because the spin waves changes, right? But can we tune one of the oscillators? That's where the programmability of these oscillators comes into picture. Now, for that, I have to go towards the voltage and memristive control of spin Hall line oscillators. Now, already in 2020, we demonstrated in our group that using the voltage control magnetic anisotropy by fabricating a voltage gate on top of a PMA tungsten CFB MGO system, we can control the frequency of these oscillators by the gate voltage. In 2022, I revised the fabrication process and fabricated a nano gate. Initially, in this work, we fabricated a micro gate on top of the SHNO. In this particular work, I basically started fabricating nano gate on top of each and every SHNO so that we can individually control them instead of having a global control over the whole magnetization. And here I demonstrate that we can have even larger frequency change using these nano gates. Now, utilizing this phenomena on the phase control mutual synchronization, we did actually micromatic simulations at that time, but now we also have experimental results of this kind, where we fabricate a gate at the bridge of between two oscillators. The bridge basically is the place where the spin waves interact. And by having a gate there, we can control the magnetic anisotropy of the bridge, changing the in-phase to out-of-phase mutual synchronization or out-of-phase to in-phase on demand using individual control at the bridge. Now, this will help us when we will fabricate large number of oscillator arrays. Now, another way to control these oscillators apart from VCMA is the memristive gating. So by just replacing the top electrode to a memristive element such as titanium, we can actually program different memristive resistances by changing the compliance currents. And this can combine two technologies, that is memristors and spin Hall line oscillators, which you can utilize to control the mutual synchronization of SHNOs. For example, here we have 4 SHNOs, and using this gate M1, when we change the voltage in the M1, we switch the low resistance to high resistance state of the memristors. And as soon as we do that, when we change from high resistance to low resistance state, this 3 and 4 oscillators start getting more current in the system compared to the first and second oscillators. Because the M1 is fabricated here, so it adds the current only to 3 and 4, bringing these oscillations to this frequency and hence a mutual synchronization. So we can basically control the mutual synchronization using memristic gating as well. Another way of programming these spin Hall line oscillators, if you don't want to have a physical gating, either memristive or voltage, you can actually do it with light. So this was demonstrated again in 2022 by Suresh Muralidharan in our group, where we showed that if you shine a laser, because of the heating of these oscillators, you can change and tune the frequency of these oscillators largely and bring it in or out of mutual synchronization if you wish to do that. Now, I have showed you two things. One, the controllability of these oscillators and the programmability of these oscillators. Now, the third important aspect is the scalability of these oscillators. So I have already showed you 51 oscillators, but actually in 2020, our group has already demonstrated up to 64 oscillators mutually synchronized in a two-dimensional array, where they have fabricated such an array where the hole separates two oscillators here, and hence you have a 64 oscillators here. And here you can see the mutual synchronization of 64 oscillators, where each oscillator is of width of 50 nanometer with a separation of 100 nanometer. Now, the key issues here are the large current, that is 6 milliamp, for just 8 oscillators gives you a large joule heating, hence more thermal agitation or thermal effects into the system. Another problem was a large separation between the oscillators, which results into a lower coupling between the oscillators. Hence, the mutual synchronization is not very robust. Now, to improve these two aspects, we researched over time and we came with two different papers that you can see here. In the first one, we optimized the spin orbit torque layer. Instead of using platinum or simple tungsten, we moved towards tungsten tantalum alloy, which reduces the power consumption by almost 60%. And then the second thing that we did is that we started fabricating very narrow SHNOs. Here I demonstrated 10 nanometer SHNOs, and combined with the large SOT of tungsten tantalum, now we can operate a single spin Hall and oscillator at about 26 to 28 microamp. Now this is extremely small. Now using this low current and small oscillators, we started fabricating extremely large array of oscillators. So here I show you two examples of 100 cross 100, that is 10,000 oscillators, and 150 cross 150, that is 22,500 oscillators with 20 nanometer width and 10 nanometer width. Here I show you a square array, but the largest one that we fabricated is we extended these columns to 700 oscillators and finally achieving a 105,000 oscillators mutually synchronizing and resulting into larger output power and lower line width of less than 20 kilohertz. Now, if you look into more carefully, if we look at how these oscillators start mutually synchronizing with number of oscillators, we see that again the line width goes with 1 by n, and the output power increases with n, which basically confirms that these oscillator arrays are robustly mutually synchronized. To confirm it further, we performed the micro BLS measurement, where we see almost equivalent intensity throughout the whole array. This demonstrates a 105,000 oscillator array, and you can see the intensity is almost equivalent, almost all over the array. There is a small changes at the edges that comes because the lead are ferromagnet, so that consumes a lot of energy. Now, with this, I come to almost my final slide where I benchmark these oscillators. So a single oscillator stands somewhere here with output power of a nanowatt and a quality factor of 1,000, but with large arrays, now we are somewhere here with almost 10 nanowatts of power and a quality factor of 1 million. With this, I summarize my today's presentation, and I hope I was able to show you that this new emerging platform of spin Hall and oscillators is scalable, controllable, and programmable, basically giving you the key ingredients for neuromorphic computing or unconventional computing architectures in spintronics domains. With this, I thank you and give the floor back to Pankaj. Thank you.
Thank you, Akash, for the wonderful talk. Now we are open for the questions. So if you have any questions from the participants, you can write in the chat box or you can raise the hand. So in the meantime, I can ask one question. You
Yes.
talk about these SHNO devices for from an application point of view for computing and all purpose. So, but you are using a current to do all these things, right?
Yes.
Yeah. So, like recently, people from Berkeley and Intel, they showed that like if we use electric fields, they make a device, I think, called magnetoelectric
Miso.
spin orbit. Yeah.
Yeah.
So, how do you see the comparison of this energy losses as compared to that device? Because they say they go like attojoule of energy consumption
I
in
mean,
the
if you
device.
look at those devices, to operate those devices, you still need current, right? The attojoule
Yeah.
is to switch the device. So there is
Yeah.
always a standing current that is going through the system. I
Mm-hmm.
think that is similar that you can obviously it will not be so efficient as MISO, but the
Hmm.
readout in MISO is also not that large.
Yeah. Yeah.
Uh, the spin Hall and oscillator stands more or less close to it, if not
Mm-hmm.
that much energy efficient. Is that you if you pass a sustained IDC to
Mm-hmm.
operate the system, you don't need to change the IDC. You don't have to play with the current. Instead, you have to again play with the voltage again. So it is similar to a magnetoelectric effect.
Yeah.
And the
Yeah.
good thing is that you can also combine memristive effects. So if you have both a memristive kind of element, you get a local control and a global control because VCMA acts on like a small one single SHNO. So if your one SHNO was out of mutual synchronization or was not, or basically led you to what we call it, the local minima, you can bring
Mm-hmm.
it or change the state by VCMA and bring it or restart the system to restart calculations and get to the global minimum. Or you can have a low resistance state memristors where you whatever charge current you pass through here, it is felt by all the oscillators that come in the way forward. So you can tune a
Yes.
large number of oscillators as well at the same time. So the
Right.
flexibility of programmability is much larger here, I would say.
Yeah, yeah, I think also from a material point of view, they only works in BFO and
Yes,
not so much of the room temperature. I start.
yes, yes,
Yeah,
yes. And
for you,
here,
it's
here,
the
and here you
advantage.
use very conventional materials.
Yeah,
There
yeah,
is nothing fancy here that I have showed you.
yeah. So we have a question from Kuldeep Ray. Yes,
Hmm.
Kuldeep, you can
Hi,
unmute and
Akash.
ask.
Thanks for your nice talk.
Thank you,
I had a
Kuldeep.
question that you have these diamond shape separators between these two oscillators. For example, in
Yes.
picture in between. How
Yes, yes.
important is the shape of this separator in improving your performance?
Okay, so it's a very nice question actually. And if you have noticed, let me go back to one of the slides here. I actually changed the shape very largely here without telling you why. And the reason comes because we are using metallic ferromagnets, so the spin waves decays much faster here. So if your bridge is very wide, as I started with 500 nanometer separation or 700 nanometer separation, the spin wave dies out very soon. And then I cannot achieve this spin wave based coupling because the spin
Okay.
waves already decayed before interacting with each other. If you want to basically extend this for smaller SHNOs that was here, it doesn't matter. If you extend it further like this or in this both of the directions, it doesn't matter because you're using, again, metallic ferromagnet. So whatever spin waves are pumped into this triangles, they already die out. The reflection is very minimal. If you go towards in future in low damping materials, then it will become more important because then you want to doesn't deal with the reflected spin waves from these sharp edges. So then you will have to either fabricate 45-degree truncated bridges, or you have to extend these bridges very largely so that the spin wave just goes and decays infinitely. So for now, it is not so important. I can even truncate it somewhere here and save some of the spin waves. But at some point of time, you have to deal with the reflected spin waves.
Okay, thank you. Thank you very much.
We have another question from Danny Dominic. So, Danny, you can unmute and ask.
Okay, thank you very much, Akash, for the nice talk. It's a really nice topic, very interesting. But I will ask for maybe an off-topic question regarding the your nano oscillators. There is how large is the mechanical resistivity of your fabrication? I mean, because you told that some of your nano oscillators were only 10 nanometers wide. So you
Yes.
had some problems regarding the fabrication or the manipulation of these nanostructures?
So you meant the electrical resistance, right?
Well, both in electrical resistance, but also with mechanical strains or something like that. You have problems with the manipulation of your samples in the lab, or they were strong enough.
No, well, mechanically they're quite strong because these are just metals
Okay.
capped with oxide. The whole optimization process to get to 10 nanometer was to optimize the etching process so that we don't break the oscillators. Because when they become 10 nanometer, their thickness and the width becomes more or less equivalent, right? So there is very large chances that mechanically they can fall out. But that usually happens during the etching process when these high energy atoms are bombarding on your spin Hall and oscillators arrays. But we optimize that process and then we optimize the resist itself so that we can have a very conformal and very high contrast resist where the sides of the resist are pretty straight instead of having like a confocal geometry, which we usually get. So the struggle was to optimize these processes. Mechanically, they are quite strong and they're very stable. You
Okay.
can work for years with these devices and they operate more or less same.
Okay, thank you very much.
Yeah.
Okay, thank you. So, if you have any other questions, you can join Akash in Agatha Town and you can chat with him. So, thank you, Dr. Akash Kumar, for this wonderful talk and accepting our invitation.